At Oroville Dam, Phase 2 of the Spillway Reconstruction project marked a decisive stage in restoring one of the most critical flood control structures in the United States. The work followed the dramatic 2017 spillway failure and focused on permanently rebuilding both the main spillway and strengthening the emergency spillway system to withstand extreme hydraulic forces. Construction teams began by demolishing damaged sections of the original spillway chute. The rebuilt structure features steel-reinforced concrete slabs averaging about 7.5 feet thick, far stronger than the original spillway floor, which had been only about 2.8 feet thick. Long rock anchors, some extending up to 25 feet into the bedrock, secure the slabs firmly to the foundation, ensuring the structure can withstand powerful water flows during major reservoir releases. The spillway chute stretches more than 3,000 feet down the steep hillside and reaches nearly 180 feet in width, roughly comparable to a multi-lane highway. Massive reinforced concrete walls along both sides guide high-velocity water safely down the channel toward the river below. Engineers also installed improved drainage systems beneath the slabs to relieve groundwater pressure and prevent uplift forces during heavy discharge. During reconstruction, large scour holes left by the 2017 incident were first filled with roller-compacted concrete. This material provided a stable base for the final structural concrete layer placed on top. The completed spillway chute now combines RCC foundation material with thick cast-in-place concrete slabs reinforced with multiple layers of steel rebar, dramatically increasing the durability of the structure. At the base of the main spillway, crews rehabilitated the massive energy-dissipating blocks known as dentates. These structures break up the powerful flow of water before it reaches the downstream river channel, reducing erosion and protecting the riverbed from extreme turbulence. Meanwhile, significant improvements were made to the emergency spillway, located adjacent to the main chute. Engineers constructed a secant pile cutoff wall consisting of hundreds of overlapping concrete piles drilled deep into bedrock. This underground barrier prevents erosion from traveling uphill toward the spillway structure if overflow ever occurs again. A large roller-compacted concrete splash pad and buttress were also built to armor the hillside and absorb the force of cascading water. Throughout Phase 2, thousands of workers and engineers operated heavy construction equipment across the massive dam site. Concrete pumps, cranes, drilling rigs, and earth-moving machines worked continuously to complete the rebuild under demanding timelines. In total, more than 1,000 workers contributed over 2 million labor hours to restore the spillway system. With the completion of Phase 2, the Oroville spillway system emerged significantly stronger and more resilient. The rebuilt infrastructure now provides improved flood protection, ensuring the dam can safely manage extreme storm events while protecting downstream communities across California. At Oroville Dam, crews completed a critical milestone during Phase 2 reconstruction of the Oroville Dam main spillway, with the placement of the final dentate structure and chute wall concrete. The dentates, large energy-dissipating concrete teeth at the base of the spillway, play a vital role in slowing high-velocity water before it reaches the river channel. Over an intensive 5-day operation, construction teams worked continuously around the clock to complete the final structural concrete placement. The process required precise coordination of batching, delivery, and finishing operations. Concrete was carefully poured into the reinforced forms, followed by mechanical vibration to eliminate air pockets and ensure full consolidation around the dense steel reinforcement. Once the structural mass was properly compacted, crews began surface finishing operations. Specialized texturing techniques were applied to create the roughened spillway surface needed to manage water flow and reduce hydraulic uplift forces during major releases. Final polishing ensured the concrete achieved the required durability and surface integrity. Quality control engineers monitored temperature, curing conditions, and alignment throughout the placement to maintain strict engineering specifications. The final dentate installation represents one of the last major structural elements in the spillway rehabilitation project, significantly strengthening the dam's flood discharge capacity. With the dentate structure completed, the rebuilt spillway system is better prepared to safely manage extreme reservoir releases, protecting downstream communities while restoring long-term operational reliability to one of California's most important water infrastructure facilities. Within the rapidly advancing field of modern bridge engineering, the casting and launching of full-span box girders represent one of the most efficient methods for constructing long elevated viaducts. This highly coordinated operation combines precision fabrication, heavy transport systems, and advanced launching technology to deliver entire bridge spans in a streamlined process. At the full-span casting yard in Anand, the production cycle begins with the preparation of reinforcement cages for the massive box girders. Steel reinforcement bars are carefully arranged and securely bound to form a rigid structural framework. This reinforcement cage provides the internal strength required for the girder to withstand both construction loads and long-term operational stresses once installed. After the cage binding process is completed, specialized lifting equipment shifts the large reinforcement structure into a precisely aligned mold. The mold is designed to produce the exact geometry required for a full-span box girder, ensuring dimensional accuracy and structural consistency across every segment. Following the positioning of the reinforcement cage, inner shutters are inserted inside the mold. These internal formwork systems create the hollow box structure that characterizes box girders, significantly reducing weight while maintaining exceptional structural rigidity. Concrete casting then begins. High-performance concrete is poured and carefully vibrated to eliminate air pockets and ensure uniform compaction throughout the entire structure. After curing, the finished girder emerges as a massive monolithic element capable of spanning large distances. Once the girder reaches the required strength, a heavy-duty straddle carrier transports the completed span from the casting yard. This specialized vehicle is designed to handle the enormous weight and dimensions of the girder, while maintaining stability and precision during movement. The girder is then transferred by a bridge gantry onto a girder transporter, which delivers the span to the launching gantry positioned along the elevated alignment. The launching gantry lifts and precisely places the full span girder onto the bridge piers. With each successful placement, the viaduct steadily takes shape, forming a continuous elevated structure that demonstrates the remarkable efficiency of full-span box girder construction technology. The Mumbai-Ahmedabad high-speed rail project represents a major leap in modern railway engineering, introducing advanced high-speed rail technology to India. Stretching approximately 508 kilometers between the cities of Mumbai and Ahmedabad, the corridor includes 12 stations and is designed for trains operating at speeds up to 320 kilometers per hour. Once operational, travel time between the two cities will be reduced to just over 2 hours, dramatically improving regional connectivity and economic integration. A defining engineering feature of the project is the extensive use of elevated viaduct structures, which account for the majority of the alignment. Construction employs the full-span girder launching method, a highly efficient technique that allows massive precast box girders, approximately 40 meters long and weighing close to 970 metric tons, to be installed rapidly using specialized launching gantries. This mechanized system significantly accelerates bridge construction compared with traditional segmental methods. Numerous bridges and tunnels are also integral to the corridor. Major river crossings, steel bridges over highways and railways, and complex underground works are required to maintain the high-speed alignment. One of the most remarkable engineering elements is the 21-kilometer underground tunnel near Mumbai, which includes a 7-kilometer undersea section beneath Thane Creek, constructed using a combination of tunnel boring machines and the new Austrian tunneling method. Track construction incorporates Japanese high-speed rail technology, including the ballastless slab track system designed for high stability and precision at extreme speeds. Specialized machines handle slab placement, rail alignment, and flash butt welding to ensure millimeter-level accuracy. Supported by advanced electrification, signaling, and safety systems derived from Shinkansen standards, the corridor represents a transformative milestone in India's railway infrastructure development. A launching gantry is one of the most critical machines used in modern elevated bridge construction, designed to install massive precast segments or full-span girders directly between bridge piers. A time-lapse view of the operation reveals the remarkable precision and efficiency behind this highly engineered system. Positioned high above the ground on completed piers, the launching gantry functions as a mobile bridge-building platform. Its long steel truss structure spans multiple supports, allowing it to lift, carry, and accurately position heavy concrete girders along the alignment of the future viaduct. During installation, a girder transporter delivers the precast span beneath the gantry. Powerful lifting winches and synchronized hydraulic systems raise the enormous element and carefully move it forward along the gantry's rails. This complex sequence appears almost effortless as the massive girder slowly advances toward its final location. Once aligned over the bridge piers, the gantry gradually lowers the girder into its exact position using controlled lifting mechanisms. Engineers continuously monitor the placement to maintain millimeter-level accuracy. After the span is secured, the launching gantry advances to the next position, repeating the process and progressively extending the elevated structure. Construction of the AR-22 East Temporary Bridge follows a structured sequence of reinforced concrete and pre-stressed girder operations designed to ensure structural stability and efficient assembly. The process begins with rebar fabrication for pile reinforcement cages. Steel bars are cut, bent, and assembled into cylindrical cages that provide the tensile strength required for deep foundations. Sacrificial piles are then driven into the ground to stabilize soil layers and guide the installation of the permanent piles. Once the pile locations are prepared, the rebar cages are lowered into the drilled shafts and accurately positioned. Concrete is then cast into the piles, forming the primary deep foundation elements. After the piles achieve the required strength, pier construction begins. Reinforcement for the pier head is fabricated and assembled, followed by concrete casting to create the structural support that will carry the bridge superstructure. For girder production, reinforcement bars are cut, bent, and assembled within casting molds. A CPF liner is installed to improve the durability and surface quality of the concrete. Pre-stressing strands are then placed and tensioned to introduce compressive forces into the girder. Concrete is poured into the mold and allowed to cure while the strands remain under tension. Once the concrete reaches the specified strength, the pre-stressing strands are gradually detensioned, transferring compressive stress to the girder. The completed box girders are transported to a stockyard for storage before installation. The SGH 20-12 CNC pile cage welding machine is designed for automated fabrication of reinforcement cages used in deep foundation piles. The system is equipped with an automatic feeding device that simplifies operation and significantly improves production efficiency. A modular template system, combining template rings with guide tubes, allows rapid adjustment of cage diameters and flexible configuration of the number of longitudinal rebars. An automated wire feeding mechanism controls the spiral reinforcement spacing, enabling precise online adjustment with minimal pitch error and high forming accuracy. The straightening system is manufactured from high-strength alloy materials, providing excellent wear resistance and extended service life for critical components. Multiple hydraulic support rollers hold and stabilize the reinforcement cage during production, preventing deformation caused by the cage's own weight. A variable frequency-controlled cage pulling mechanism ensures smooth movement and high positioning accuracy throughout the welding process. Automatic pile cage welding systems streamline the fabrication of reinforcement cages used in deep foundations and board piles. Steel rebars are automatically aligned, rotated, and welded with high precision, ensuring consistent spacing and structural strength. This automated process improves productivity, reduces manual labor, and delivers uniform reinforcement cages for large-scale infrastructure and construction projects. At the redevelopment of the multimodal transport hub around Gare de Lyon-Pardieu, foundation specialists acted as joint contractors responsible for complex retaining structures and deep foundation works. The project includes a 5-level underground parking structure, a new station hall, and the 170-meter-high Rotow Tower. For the parking place bassin excavation, diaphragm walls and barrette foundations were constructed to stabilize deep excavation zones and support the surrounding infrastructure. Approximately 18,000 cubic meters of reinforced concrete were placed during these structural works. Ground stabilization was further reinforced through pressure grouting operations, combined with the installation of about 1,000 micropiles, reaching depths of roughly 35 meters, ensuring adequate load transfer and settlement control in challenging soil conditions. The foundation system for the Rotow Tower required high-capacity deep piles installed using the Starsol F5000 piling system. A total of 120 foundation piles were drilled and constructed to transfer the massive structural loads of the 170-meter skyscraper into stable subsurface strata. This advanced deep foundation solution guarantees long-term stability, structural integrity, and safe performance for one of Lyon's most prominent urban redevelopment projects. During the expansion of the I-4 Ultimate Freeway expansion for the Florida Department of Transportation, large drilled shaft foundations required the installation of extremely long reinforcement cages, measuring up to 148 feet. These cages were assembled using the HRC 500 series coupler mechanical splicing system, designed to provide high structural performance and simplified field installation. The HRC 500 series system is engineered to exceed the mechanical requirements of ASTM 706 and ASTM 615 reinforcing steel. The couplers are specified to achieve approximately 175% of the steel yield strength, ensuring that the connected reinforcement maintains full tensile capacity, compressive strength, and ductility even under cyclic or plastic loading conditions. This level of performance is critical for deep foundation structures subjected to dynamic traffic loads and long-term structural stresses. Installation begins with the placement of the first drilled shaft reinforcement cage section into the excavation. The next cage segment is then lowered and aligned above the installed section. Workers connect the reinforcement bars by bringing the cages together and engaging the threaded couplers by hand. Once the initial connection is made, a wrench is used to tighten the coupler and apply the required torque, creating a secure mechanical splice. One advantage of the HRC 500 system is its adaptability to challenging field conditions. If small gaps exist between bars, tightening the coupler can draw the reinforcement together and close the distance. The coupler can also accommodate slight angular misalignment or curved reinforcement, allowing bars positioned at a radius or angle to be successfully connected. During tightening, the reinforcement bars gradually realign within the coupler, ensuring proper load transfer across the splice. This simplified connection process reduces installation time while maintaining strict quality control. The mechanical splice system therefore enables fast, reliable assembly of extremely long reinforcement cages used in deep, drilled shaft foundations for major highway infrastructure projects. The construction of the Luma Arles Tower stands as one of the most ambitious contemporary architectural projects in southern France. Construction of the building took place between 2014 and 2021. The tower rises approximately 56 meters above the historic city of Arles and is immediately recognizable for its striking, irregular geometry. Inspired by the rugged limestone formations of the nearby Alpilles Mountains and by the dynamic brushstrokes found in the paintings of Vincent van Gogh, the design features a fragmented facade composed of thousands of reflective metal panels. Construction required advanced engineering techniques due to the complex architectural form. The project began with the creation of a large, cylindrical glass drum at the base of the tower, which houses exhibition spaces and public areas. This transparent volume supports the rising tower structure above it. The superstructure consists of a reinforced concrete core surrounded by an intricate steel framework. This structural skeleton allows the building to achieve its dramatic twisting geometry while maintaining stability and resistance to wind forces. Digital modeling and precision fabrication played essential roles in producing the many uniquely shaped facade panels. More than 11,000 stainless steel panels were installed to form the tower's shimmering exterior. Each panel was carefully positioned to create a constantly shifting play of light across the surface, reflecting the colors and atmosphere of the Provençal landscape. After 7 years of design and construction, the tower opened in 2021 as a landmark of contemporary architecture. Today, the Luma Arles Tower serves as a hub for exhibitions, artistic collaboration, and cultural innovation, marking a bold new chapter in the architectural identity of Arles. Following the construction of Switzerland's earlier landmark skyscrapers, the Prime Tower in Zurich and the Rotow Tower in Basel, a new chapter in Swiss high-rise engineering emerged with the development of Rotow Tower 2. The construction site was cleared in early 2017, marking the beginning of an extremely demanding urban engineering project. Excavation reached a depth of approximately 20 meters, forming a large foundation pit in the densely built city center. Once excavation was complete, construction of the massive base plate began. This foundation slab measured approximately 2.5 meters in thickness and required enormous volumes of concrete. The base plate and basement floors together provide the essential weight and structural stability required for the tower above. In 2018, the ceremonial foundation stone was placed and permanently embedded within the concrete. Due to the extremely limited space available at the city center site, the entire construction infrastructure, including offices, material storage, and even a concrete plant, had to be carefully arranged within a confined area. The project schedule was highly ambitious, and construction sequences were analyzed in advance using Building Information Modeling (BIM) to ensure logistical feasibility. The tower's structural system was built around a reinforced concrete core containing staircases, elevator shafts, and service ducts. Construction began with the core, followed by floor slabs that extended outward from it. In September 2018, an automatic climbing system was installed to form and support the rising core structure. Acting simultaneously as formwork, scaffolding, and working platforms, the system climbed upward after each concreting cycle. Each construction stage measured nearly 4 meters in height. After concrete hardened, hydraulic cylinders lifted the formwork to the next level, allowing reinforcement to be installed and new concrete to be poured. Through this process, the tower steadily rose, initially 1 floor every 14 days, later accelerating to roughly 1 floor every 10 days as operations became optimized. Powerful concrete pumps delivered material from the on-site plant, eventually pumping concrete more than 200 meters upward. At the same time, floor slabs spanning up to 10 meters were constructed and heavily reinforced. Despite severe space constraints, prefabricated components, including stairs and facade elements, arrived precisely on schedule and were installed directly from delivery trucks. As construction progressed, facade installation and interior technical systems advanced simultaneously on lower floors. By autumn 2020, construction had reached nearly 200 meters. The final stages progressed at remarkable speed, with new floors completed roughly every 6 days. In November 2020, the last floor slab was finished, marking the completion of the tower's structural core. Rising above the skyline of Basel, Rotow Tower 2 now stands as the tallest building in Switzerland, and a defining feature of the city's modern architectural landscape. Rising on the Red Sea coast in Jeddah, construction of the iconic Jeddah Tower advanced steadily between January 2015 and April 2016. During this period, massive reinforced concrete cores and deep foundation piles formed the backbone of the megastructure. Precision slipform systems, high-strength concrete, and carefully coordinated crane operations enabled rapid vertical progress, laying the structural groundwork for what is designed to become the world's tallest skyscraper. The replacement of the Dickenson Creek Bridge represents a significant infrastructure upgrade designed to enhance safety, structural capacity, and long-term transportation reliability. After decades of service, the original bridge had begun to show signs of aging and structural fatigue, making a modern replacement necessary to meet current engineering standards and increasing traffic demands. Construction of the new bridge begins with the preparation of foundations and supporting structures. Engineers first stabilize the site and construct reinforced concrete abutments and piers that will support the bridge superstructure. These components are carefully aligned using precise surveying equipment to ensure the structural elements of the bridge will fit together with exact accuracy. Once the substructure is complete, attention shifts to the installation of the main bridge girders. A specialized gantry crane is deployed to perform this critical task. This massive lifting machine operates above the bridge alignment, designed specifically to handle extremely heavy precast girders. Each girder is carefully lifted, transported, and positioned onto the bridge piers using synchronized lifting systems. The gantry crane slowly moves along the structure, installing one girder after another until the primary structural framework of the bridge is fully assembled. With the girders securely in place, the next phase focuses on constructing the bridge deck that will carry the roadway surface. Workers begin by installing reinforcement bars and formwork across the top of the girders, creating a platform ready for concrete placement. This reinforcement grid strengthens the deck and ensures the finished surface can safely support vehicles, trucks, and daily traffic loads. Concrete is then poured evenly across the prepared deck surface. To achieve the required smoothness and structural integrity, construction crews use a long, vibrating screed machine. This specialized finishing equipment travels slowly across the deck, while vibrating and leveling the freshly placed concrete. The vibration removes trapped air pockets, while the long screed beam ensures the surface remains uniformly flat across the entire bridge span. As the screed progresses, the deck surface becomes increasingly smooth and evenly compacted. Additional finishing work may be performed to refine the texture and ensure proper drainage characteristics. After the finishing process is complete, the newly placed concrete deck is carefully covered to protect it during curing. This protective layer helps maintain proper moisture levels and temperature conditions, allowing the concrete to harden gradually without cracking. The deck is then left undisturbed overnight. By the following day, the concrete has gained sufficient strength to allow further construction work to continue, bringing the new bridge one step closer to completion and providing the community with a safer, more durable crossing for decades to come. At Hososhima Port, large 80-ton Dolos wave-dissipating blocks are manufactured to strengthen coastal protection structures. These massive concrete units are designed to absorb and disperse the force of incoming waves, helping safeguard harbor infrastructure and shoreline facilities. Production begins with reinforcement assembly. Prefabricated steel bars are delivered to the yard, coated with anti-corrosion agents, and assembled into complex reinforcement cages. Formwork is then installed and secured with bolts and cotter pins. Concrete is pumped into the molds and compacted to remove air bubbles and surface latents. After placement, Curing compounds are sprayed to protect the concrete while it gains strength. Once the required compressive strength is reached, the molds are removed and the completed blocks are repositioned for storage and future installation. In the field of tube and pipe manufacturing technology, SMS Group is recognized for highly engineered production systems used to manufacture large-diameter steel pipes. A notable example is the Vysota 239 pipe plant operated by Chelpipe Group in Chelyabinsk, designed specifically for high-performance production of pipes used in oil and gas transmission pipelines. Production begins with the preparation of steel plates that will later form the pipes. Incoming plates undergo a series of quality control procedures including visual inspection, ultrasonic testing, and sandblasting. These operations verify internal material integrity while removing surface impurities that could affect welding performance. The plates then enter a precision edge milling machine where both edges are machined to exact tolerances. This step produces parallel edges and carefully controlled bevel angles, which are essential for achieving high-quality weld seams during later welding stages. Following edge preparation, the plates are transferred to the forming section, where the JCO forming presses gradually bend the flat plate into a cylindrical pipe shape. Unlike conventional forming systems, the JCO method shapes the pipe step by step through sequential pressing operations. This technique significantly reduces forming forces while ensuring accurate roundness and dimensional consistency, even when the steel plate exhibits variations in mechanical properties. The Chelyabinsk plant operates two forming presses with different stroke lengths. The 18-meter press is primarily used to produce long pipes for extensive overland pipeline networks common in Russia, while the 12-meter press is optimized for smaller diameters and thick-wall offshore pipeline applications. After the pipe shell is formed, it moves to tack welding stations, where hydraulic roller beams precisely align the plate edges. A continuous tack weld temporarily secures the seam before the pipe enters the final welding stage. Internal and external seam welding is performed using submerged arc welding technology. Multiple welding wires may be used simultaneously, creating deep penetration welds with excellent mechanical properties and consistent seam quality. To ensure structural integrity, each pipe undergoes several stages of non-destructive testing. Ultrasonic and X-ray inspection systems analyze the weld seam and pipe body to detect internal flaws or material discontinuities. Next, the pipe passes through mechanical expanders that calibrate the diameter and straighten the structure. This critical step improves dimensional precision while enhancing the mechanical characteristics of the steel. Additional finishing processes include pipe infacing and chamfering, preparing the pipes for welding during pipeline installation. Each finished pipe is then subjected to hydrostatic pressure testing, where water pressure verifies strength and leak resistance under simulated operating conditions. The entire production line is coordinated by an advanced manufacturing execution system supplied by SMS Group. This automation platform tracks every pipe throughout the process, records quality data, and generates complete certification documentation. With an annual capacity approaching 900,000 tons, the Chelyabinsk facility represents one of the most technologically advanced large-diameter pipe manufacturing plants in the global pipeline industry. Steel production at Grupo Seismic relies on integrated electric steel making and automated rolling technology. Recycled steel scrap is melted in electric During rolling, the billets pass through multiple stands where precise mechanical deformation forms reinforcing bars, wire rod, and structural profiles. Automated control systems regulate temperature, rolling speed, and dimensional tolerances to ensure consistent metallurgical properties. Advanced finishing lines perform cooling, straightening, and cutting operations according to customer specifications. Quality control includes dimensional inspection, mechanical testing, and metallurgical analysis to guarantee compliance with industrial standards. Through these controlled processes, steel scrap is efficiently transformed into durable structural materials for construction and industrial manufacturing. The construction of the seismic-resistant Quay wall in the Yokohama port involves the precise installation of large steel arc segments used in the steel plate cellular quay structure. This complex marine engineering operation is carried out as part of the development of a new deep-water berth designed to accommodate vessels with drafts of up to 18 meters. Once the morning safety briefing is completed, work begins immediately as the transport barge carrying the first arc segment arrives at the construction site. The massive steel arc component had previously been fabricated at a production yard in Futsu. There, a 300-ton floating crane loaded the segment onto the barge before it was towed across Tokyo Bay to the Shinhonmoku construction area. Upon arrival, lifting equipment is attached to the arc using rigging slings connected to the dedicated installation frame. Once the crane lifts the heavy steel arc, the barge is slowly pulled away, allowing the component to be positioned for installation. The arc is carefully lowered between an existing steel plate cell and the first newly installed cell of the Quay structure. Workers then guide the arc into the arc joint connectors that had been previously installed on the steel plate cells. This is an extremely delicate operation requiring precise control to maintain perfect horizontal alignment as the arc is inserted into the joints. After careful positioning, the first arc segment smoothly reaches the seabed and lands successfully in its designated location. Following this, a vibro hammer, mounted on the installation frame, is lowered into position. Hydraulic clamps grip the arc securely, and the vibro hammer is activated to perform fine vertical adjustments until the segment reaches the specified elevation. With this operation, the installation of the first arc is successfully completed. The lifting process then begins for the second arc segment. By this time, wind conditions have intensified, causing the suspended arc to sway more noticeably. Crane operators must rotate the component very carefully to prevent uncontrolled movement. As the arc approaches the designated position, a Y-shaped guide installed at the top of the arc joint helps align the component. Using these guides on both sides, the crew gradually inserts the arc into the joint connection. Once the segment touches down on the seabed, the vibro hammer is again used to adjust the elevation precisely to the planned installation level, completing another critical step in the quay wall construction. The dismantling of the former fuel storage facility, operated by McGraw, was a major industrial demolition and environmental remediation project located at Tosreden am Rhein. The site once stored up to 40 million liters of fuel, requiring careful planning to safely remove infrastructure while preventing environmental contamination. The project began with the demolition of large cylindrical and cubic reinforced concrete tanks, each with a capacity of about 600 cubic meters. Before the structures could be dismantled, the internal protective coatings and the upper contaminated layer of concrete were milled off. These materials were collected separately and disposed of through specialized waste treatment processes to ensure safe handling of hazardous residues. Excavated materials from the site were carefully sorted through an on-site triage process. Clean concrete and contaminated soil were separated to allow proper treatment. Depending on contamination levels, materials were either transported to certified landfills, treated thermally, or sent to the ESAR soil washing facility for environmental processing. Another major task involved removing underground steel storage tanks. A total of 174 tanks measuring between 21 and 40 meters long and about 3 meters in diameter were excavated. Temporary road widening was required to accommodate heavy transport vehicles removing the tanks from the site. Of these tanks, 114 were transported for professional decontamination and recycling, while 60 were dismantled directly on site before being sent for material recovery. After demolition was complete, the 25,000 square meter site underwent renaturalization in cooperation with regional environmental authorities.